Hello everyone, welcome back to the third session on power system analysis. In this session, we are going to solve some numerical problems related to the symmetrical components. Let us start with the problem number 1. So the problem statement is like this. Prove that a balanced set of three-phase voltages will have only positive sequence components of voltages only. Okay, so from this statement, what we understand is that let us consider a balance system like this. So when you are going to say the balance system, the given system is balanced when all the magnitudes are equal to each other. So the magnitude of voltage VA, the voltage of VB and VC have to be equal to each other. So that is given in our solution part over here. So if the magnitude of all the three phases are equal to each other and they are displaced by an angle 120 degree apart from each other. Okay, so this is our balanced system and these are the balanced voltages VA, VB and VC. Okay, so for these voltages we need to prove that it will have only the positive sequence component. So the whatever the voltage we are going to find, it will consist only the positive sequence component of that voltage value. Okay, so as we assumed, VA, VB and VC are what? The balance systems of three phase voltages. Okay, so according to that, so let us consider VA as the reference vector. So if I consider VA as a reference vector, so VA is equal to VA at an angle. What is the angle we are going to get? Yeah, obviously it is a reference, right? So it does not have any angle over here. And VB. Okay, so as we consider VA as a reference vector, so with respect to VA, the voltage VB is making an angle of how much? Yeah, 120 plus 120, so that is nothing but 240 degrees, having an magnitude 1. As we assumed, the given system is balanced, so all the magnitudes are equal to each other. So according to that, so the angle now it will be how much? 240 degrees and the magnitude is 1. So how you are going to represent with the help of A operator? So for A operator, if the given angle is 240 degree, we are going to represent it by A square, which we studied in our previous session. Is it so? So wherever the 240 degrees are there, having a magnitude 1, so we are going to represent it by what? A square. And similarly, next one is what? Voltage VC. So from this phasor diagram, we see the voltage VC is making an angle of 120 degree with respect to VA. Is it so? So what is the A operator representation for 120 degree as we studied in our previous session? Yeah, that is nothing but A. Okay, so A represents what? A magnitude of 1 having an angle 120 degree with respect to what? Reference vector VA. So these are the two phase voltages are determined in terms of any one phase. Okay, so we consider here a phase as what? A VA. Is it clear? So this is the equation, matrix equation we obtained it in our previous session. Okay, so here we converted the symmetrical component in terms of what? Phasor voltages. So like that we need to convert over here. So let us consider this equation which we obtained it in our previous session. After that, then in this matrix, this submatrix VA, VB and VC voltage values are there, right? So we are going to replace it by these values, whatever the values we obtained with the help of this phasor diagram. So we are going to represent or replace these voltages with respective values. Okay, so after that, as we know, what we did over here, so we substituted that respective values in this equation 1. Okay, so here VA is equal to va, that's what we got. vb represents what? A square into va, and vc represents a into va. Now after do this after that do the further simplification. Here what can be done? Yeah, we can do the matrix multiplication of these two sub matrices. Okay, so va into, yeah, respectively row into column. So 1 into va plus next is what? uh, 1 into a square into va, then next one is what? 1 into a into va. So this will give one term. So v 1 into va plus 1 into a square into va plus 1 into a into va. So this is the first value we are going to get. Then after that, multiply this second row with this entire column. As we are having only one column over here, so we are going to multiply with this only one column values. Okay, so according to that, 1 is multiplied with what now? va. So 1 into va plus a is getting multiplied with this second value, so a into a square into va. So a square into a is nothing but a cube. Yeah, a cube into that remaining value is va. Then a square is getting multiplied with this once again a value, so a square into a is nothing but a cube into va. Now similarly multiply this third row now. Okay, so 1 into va, so that is nothing but va. Then a square into this second value, a square into a square is nothing but a to the power 4 into the coefficient values, that is va. Yeah, then a is multiplied with a, so a square into the its coefficient va, so a square into va. So we are going to get this matrix after multiplying these two sub matrices. Okay, so after that by using the a operator notation, so which we derived in our previous sessions, so let us consider wherever a cube is there, so we are going to represent its respective value. So in previous session we proved that a cube will be equal to what? 1, and similarly a to the power 4 will be equal to what? A, and wherever a cube and a4 are there in our this sub matrix, we are going to replace it by the respective values now. Okay, so let us identify those values over here. Okay, in first equation let us find, yeah, where, yeah, in second row we are having two a cube values, so a cube is nothing but 1, so replace it by the respective value 1. And in third row we are having a to the power 4 over here, so a to the power 4 is nothing but a, so there you replace with by a value. So after that we are going to get this simplified simplified matrix. Then let us see what can be done further now. Now let us take va as common from this sub matrix. So if I take va as common, what is left over? So 1 its coefficient e will be 1, so 1 plus, and this term coefficient is a plus this values coefficient is nothing but a square. So we are going to get va into 1 plus a square, and if I add va plus va plus va, we are going to get obviously 3va. And similarly here we are going to get the sub matrix by va into the bracket 1 plus a square. Okay, so let us see further what can be done now. And this value for 1 plus a square which we arrived at the conclusion that it will be equal to what? 0 in our previous session. We are going to use this respective value wherever necessary. Okay, so this was the equation, previous equation we simplified it, right? So 1 plus a square is nothing but it is equal to 0. So here we are going to represent this entire term by 0. So if va is multiplied by 0, it will become obviously 0. If you multiply anything with the 0 value, you are going to get 0 only. So va into 0 like that va into 0. So you are going to get two zeros in this sub matrix. So which is further simplified to what? So 0 3 va into 0. So now multiply this 1 by 3 with this entire sub matrix. So if I multiply, so it is 1 by 3, right? So 1 by 3 into 0 0. So 1 by 3 into 3 va. So 3 will get cancelled. We are going to retain only va, and 1 by 3 into 0 is nothing but 0. So if I simplify this entire matrix, so 0 sequence component. So how you are going to identify 0, positive and negative sequence component? By its respective subscripts, right? So 0 represents 0 sequence component, 1 represents positive sequence component, and 2 represents negative sequence components, which we studied in our previous sessions. So if I simplify this further main matrix, so 0 sequence components voltage we are going to get as what? 0. And the positive sequence component voltage we are going to get as a phasor voltage va, and negative sequence component voltage we are going to get as 0. So this is the proof we have made. So positive, only the positive sequence component is having the voltage value as compared to 0 sequence component, and negative sequence components are both are equal to what? 0. Okay, let us look into the another problem related to the sequence component. So from this problem statement, he has to find us the he has to determine the sequence component of the three voltages. So these are the three voltages given: VA, VB, and VC. Those are nothing but our phasor voltages. For these phasor voltages, we supposed to find out the sequence components of the particular value voltages. Okay, so which means sequence components means we are having three sets of sequence components. So those are nothing but positive sequence component, negative sequence component, and zero sequence component. So we need to find out the positive sequence components voltage, and respectively the remaining sequence components voltages we need to find out. Okay, so these are the equations we obtained from our previous session for the expression of symmetrical components in terms of phasor voltage. So these are the symmetrical components which we expressed in terms of what? Phasor voltages. So these are nothing but your phasor voltages. VA, VB, and VC are nothing but phasor voltages. We represented symmetrical component in terms of phasor voltages. So we are going to use these symmetrical these formulas to find out the respective sequence component voltages. So let us find the positive sequence component voltage. Okay, so this is the formula we are going to use to find out the positive sequence component voltage. So that is nothing but VA is equal to 1 by 3 into VA plus A into VB plus A square into VC. So with the help of this formula, so let us solve the given problem. So 1 by 3 VA. So what is the value of VA given in our problem statement? 200 at an angle 0 degrees. So substitute that value. Then what is the value of VB is given? So VB is 200 at an angle 240 degree. So 200 at an angle 240 degree. And what is the value of A operator? We are having 1 at an angle 120 degree, right? So having a magnitude 1. So we are going to add up the degrees over here, angles over here. So 240, and A operator's angle is how much? 120 degree. So 245 plus 120 degree, then plus A square into VC square. So what is the value of VC given? 200 at an angle 105 degrees. So 200 at an angle 105 degrees. And what is the value of A square? Yeah, 1 at an angle 240 degrees. So as the magnitude is 1, so no 200 into 1 at an angle. So we are going to add up these two angles now similarly. So 105 plus 240 degrees. So 240 is nothing but the angle meant for A square. So 105 plus 240 degrees. So if you further simplify these values, you are going to get the positive sequence component voltage as this much. Is it clear? Now similarly, let us find the zero. Okay, so here we are going to find out the negative sequence component voltage. So for that, the equation we are going to use is this one. So va2, so 2 represents what? Negative sequence component voltage. So va2 is equal to 1 by 3 into va plus a square into vb plus a into vc. So these are the values of va, vb and vc given in our problem statement. Is it so? So now respectively substitute the values of these phasor voltage wherever necessary, and a square value is represented by what? 1 at an angle 240 degree, and a value is nothing but 1 at an angle 120 degree. So here I substituted the value of a as 200 at an angle 0 degree plus VB value is 200 at an angle 245 degree, and that is what I written over here, 200 at an angle 240 degree. We need to add only degrees over here, don't add this real term also. So we are going to add only the imaginary terms. Is it clear? So 240 degree plus 45 degree, and this a square value is nothing but 240 degrees. So 245 plus 240 degree we are going to add up. Similarly, the VC value is given as 200 at an angle 105 degree, and the A value is nothing but 120 degree. So we are going to add up these two degrees. So if you simplify it further, we are going to get the negative sequence component voltage as this much. Similarly, so next what we need to find? The zero sequence component voltage. So what is the formula we are going derived in our previous session? So this is the formula we derived in our previous session. Is it correct? So zero sequence component voltage is given by what? 1 by 3 va plus vb plus vc. So now substitute the respective phasor values in this equation. So in this equation we are not going to use any a operators in this equation for this zero sequence component. So directly now substitute all the phasor voltage values given in our problem statement in this equation to get the zero sequence component voltage. So this is the final solution we are going to get for the given problem. So hope everything is clear. So if you are having any doubt regarding any problem related to the sequence component, please free to ask. Thank you.